Hey guys, this is the fourth of our Schrodinger model lecture series, and today we're going to try and kill two birds with one stone. That is, we'll try to get through noble gas notation, and the second thing is how to work with ions using the Schrodinger model. So what we're going to do today is the first of two things is we're going to work on noble gas notations. It's also known as the gas core convention, or the way to do things. So here's the concept. When you're writing out these electron configurations, they get kind of long and messy. 1s2, 2s2, 2p6, 3s2, 3p6. Oh, it gets kind of boring after a while, doesn't it? Because nothing cool happens until the very end. Do the next one, whatever element this is, 1s2, 2s2, 2p6, 3s2, okay. So you see the same thing over and over and over again, and here's another one. And then you see a variation only out here. So what about if we just focus on the variation, and besides that, that's where the chemistry takes place. Those electrons in the outer reaches here, those are called valence electrons, and those are the ones that are shared to make a bond or given away or taken in to make ions. So the interesting stuff is up here. How about if we just sort of ignore this and call this, well, I suppose we could call it X or any other variable letters that you like, maybe R or P or Q, I don't know. Just, something here, and then interesting stuff. Well, here's what you do, is you find the biggest noble gas that would fit in here, and grab your periodic table. There's helium, neon, argon, krypton, xenon, and radon. So what do they look like? Helium has 2 electrons, so 1s2, and we're done. Neon has 10 electrons, so we'd write 1s2, 2s2, 2p6. Write down argon, 1s2, 2s2, 2p6, 3s2, 3p6. 2p6, this one's 3p6. Let's try this next one, krypton. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, that's weird, and then 4p6. Wait, we have a definite, there's something going on here. This one ends in a p6, this one ends in a p6, and this one ends in a p6. Guess what xenon ends in? Some sort of p6. p6. Well, neon is in the second row of the periodic table. It ends up in a 2p6. Argon is in the third row. It ends with a 3p6. Krypton is in the fourth row. Take a look at your periodic table. It ends in a 4p6. Xenon, well, it's in the fifth row. It ends in a 5p6. And radon, I bet, ends in a 6p6. So let's pretend that you have that memorized right now, because after you work with this for a while, you will. So, all right, take your periodic table and write these right in there. Neon ends in a 2p6. Argon ends in a 3p6. So what we're going to do is, instead of writing out neon like this, we're just going to write down a box and write down Ne, okay, with a box with little brackets, with brackets around it. And from now on, any element that's bigger than neon, but smaller than argon, we're just going to write down Ne in a box. And you and I are going to both remember that that really means 1s2, 2s2, 2p6 is already done for us. You probably can figure this out. Argon, instead of writing 1s2, 2s2, 2p6, 3s2, 3, for atoms just a little bit bigger than argon but smaller than krypton, we're just going to write down Ar and put our brackets around it like that. And you know and I know that argon ends in a 3p6. Krypton, we're going to have brackets around it, and that means that box represents everything from 1s2 all the way up to 4p6. All right, xenon, same thing, xenon. All right, that ends in a 5p6. So some atom bigger than xenon and smaller than radon, we can just show as Xe, and then we'll add a little bit onto it. So these are called these are going to be the gas cores when we put these little boxes, brackets around everything. All right, so helium could be used as a core for anything bigger than helium, smaller than neon. Grab your periodic table. So we could use helium as the core for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and even neon. Look at this example here, strontium. I've written down the whole thing. But you know and I know that it's all the same stuff down here at the beginning. But at the end, that's where it gets interesting. Table, what noble gas comes right before Sr? So Sr is way over on the left side of the periodic table, sort of bottom left. And let's see, it is 2 bigger than krypton, Kr. So, and krypton ends in, let me see, 4p6. Look at your periodic table and see if that's not right. Krypton ends in a 4p6. It's the fourth row across, ends in a 4p6. So everything here, all the way up to 4p6, there it is, right there, that. All that business right there. We don't have to write all that. If we just write down Kr, okay, because that's krypton, put the box, the brackets around it, and then strontium is 2 bigger than krypton. Krypton is 36, and strontium is 38. Look back at your arrow diagram, or look at the beginning of your packet, and it'll say what comes after 4p6. Now I'm just going to cheat. I'm going to look up here. But on 4p6, there's 4p6, oh, 5s, and then 4, okay, 5s. 5s. I need 2 more electrons. Wait, actually, I could have just looked here because I already wrote it out. 5s, I need 2 more electrons. Can I fit 2 into an s? Sure I can. 5s2. Boom. Nailed it. Let's try another one. The vanadium, V. Okay, it's in the, let's see, it's right here. Vanadium. It is number 23. Make a note to myself, 23. What noble gas comes right before number 23, vanadium? Go back. Ti, Sc, Ca, K, all the way up. It's argon. Okay, so it's going to be an argon core, Ar, brackets. All right? And argon ends in a 3p6. Note to self, it ends in a 3p6. Argon is 18 big, 18 electrons. Vanadium is 23, so that's 5 bigger. So we have to go 5 bigger than argon. Argon ends in a 3p6. After 3p comes 4s. Can we fit 5 electrons into the 4s? Nope. We can only fit 2. Okay, so after the 4s comes the 3d. We still need 3 more electrons. 3 more electrons. Can the 3d hold 3? Yep. 3d can hold 10. So we only need 3, so we're done. Argon core, 4s2, 3d3. All right, so I said we're going to try and tackle 2 concepts today. The second concept we'll try and tackle is this, working with ions. So we've already talked about ions this year, so it shouldn't be really too difficult once you remember what an ion is. There's 2 kinds of ions. There's cations and anions. Cations, we spell it Ca+, ion, and that reminds us that it has a plus charge. And to become a cation, it's lost electrons. To become an anion, a negatively charged atom, it must have gained electrons from somewhere. So, let's see, ions are charged atoms. They have either lost or they have gained electrons, but not protons or neutrons. Only electrons, okay? Cations have a positive charge, anions have a negative charge. Oh, I should have written cation with a plus here, shouldn't I? Ca+ ion. Write electron configurations for these. Lithium with an equal number of protons and electrons. Here we go. Lithium has 3, so 1s2, 2s1. That's how it's supposed to be. But what about if it ionizes into a plus charge? To get a plus charge, it has to the atom throws away, or gets rid of, or loses 1 electron. So if it loses an electron, it has 1 less than 3, which is 2, of course. So we just write down Li plus, its electron configuration is 1s2, and we're done. How about chloride? Cl minus. All right, so chlorine has 17 electrons, 17 protons, therefore 17 electrons. But to get a negative charge, it must gain an electron from somewhere, so it has 18. 18 electrons. So stop me when I get to 18. 1s2, 2s2, 2p6, 3s2, 3p6. Stop! I think that's 18. 2, 4, 10, 12. Yes, that is indeed 18. That is the electron configuration for chloride ion, which is a chlorine atom, which has gained 1 extra electron. Now, if we wanted to, we could also make this in the gas core convention. We could use this all the way up to here. Instead of writing 1s2, 2s2, 2p6, we could recognize, oh, that's neon. And we could have replaced this with Ne in brackets, if we wished. This is kind of a small atom, and writing Ne is not that much shorter than writing 1s2, 2s2, 2p6. So it's your option usually if you want to write down Ne or if you want to write down the full 1s2, 2s2, 2p6. When we get to great big atoms, then you definitely do want to do the noble gas core convention. Iron 3 ion. How many electrons do you need for that? Iron 3. Well, iron is supposed to have 26 electrons, but if it has a +3 charge, it's thrown away 1, thrown away 2, thrown away 3 electrons. So it had 26, threw away 3, now it has 23 electrons. So you do 1s2, 2s2, all the way up until you get to 23, and you're done. Let's try one more down here, selenium with a charge of -2. Selenium, all right, it's right below oxygen and sulfur. It's got 34 electrons. It's supposed to have 34 electrons, but it has a -2 charge. It's gained 2 more. So it's supposed to have 34, gains 2, it has 36. So you go ahead and go 1s2, 2s2, 2p6, like that, all the way until you get to 36. Sorry, I think I said 26, I meant 36. Stop when you get to 36, and you're done. And that is today's lesson. The last thing we did was we worked with ions, charged particles which either have more or less electrons than you expect. And just before that, we did the noble gas convention, which is a way to make these huge, long electron configurations shorter. But you have to remember what all the noble gases end with. So hopefully you've written that on your periodic table, a little crib note. And neon ends in a 2.